Uh, Mute, huh? Hopefully, अच्छे चावल. अगर चाहिए आपको तो मेरे पास है हेडफोन.
अब देखो आ रही है आवाज आ रही है ऑडिबल ऑडिबल ऑलराइट. Hello and welcome to all the participants who have joined us. Apologies for not being able to start the session on time because of huge rush of the participants. Actually, we had already conveyed to all of you that we have a limited participation of 100 people only. So we were just filtering the participants. Anyway, it's a moment of immense pleasure and delight for all of us here at Geotechnical Engineering Division to host you, and more importantly, to connect with the researchers, the academicians, the experts in these tough times of COVID-19, when the physical learning spaces have actually been closed. So as students, we all feel that, we have lost a lot of time to this COVID-19. From the academic perspective, we see a lot of, time has been lost. So in order to, mitigate this loss, it's time to move on, to pick up from where we had actually left, and to revive and resume the academic activities. And STCs, workshops, webinars of this kind have a large role to play in resuming the academic activity. In this backdrop, we at NIT Srinagar Civil Engineering Department have organized this STC. We have pinned a lot of hopes with this. We have invited, eminent, renowned people from the concern to this field. The theme, as you already know, is Advances in Geotechnical Engineering for Sustainable Development. It's time to, open up this inaugural session. I would like to invite the coordinator of this STC, Professor B.A. Mir sir, Honorable Secretary, IGS Chapter Srinagar. Professor B.A. Mir sir has been involved through and through in this in the organization of this workshop, and it's by dint of his efforts that we are finally here. I request Professor B.A. Mir sir to preside over the session. Over to you, sir.
Hello, am I audible?
Yes, sir, you are. Please go ahead.
Thank you very much. Thank you very much. At the outset, actually, I very much, I can say, either confused because of too rush. Respected dignitaries, I think our worthy director could not join because of too much of flow. Our head, Professor Manzoor Ahmed Angar Sahab, our TQ coordinator, Professor Wani, Professor Shahid, Professor Fayaz Ahmed Sahab, Professor Shah Sahab, and dear colleagues, participants, I welcome you all for this short-term course on the inaugural day. Now, during this COVID-19 pandemic, everything has derailed, and this is the only medium that we can connect each other. Now, as far as this short-term course is concerned, I thank our worthy director who ignited us for conducting this course despite very busy schedule. And I took this challenge keeping two things in mind. The geotechnical engineering is very close to my heart because it offers interactive challenges. If what we did yesterday is wrong for today, and what we will do today is not valid for tomorrow, and what is to be done tomorrow is very uncertain. This is one important thing. Second thing is that because of rapid increase in population and other infrastructures, there is a scarcity of good construction sites or suitable sites, and there is a lot of pressure on geotechnical engineers to utilize marginal or weak or problematic soil deposits. Also, there are a lot of waste materials produced, and if not scientifically disposed of, may create a lot of environmental and health problems. So, therefore, clubbing these two things together, we need to have a sustainable solution, and hence this course is named as Advances in Geotechnical Engineering for Sustainable Development. And in this case, I am pleased to share with you that I have very eminent speakers for this short-term course, and I thank them that they have accepted our invitation. And I hope that all the participants will get benefited throughout this course as we go ahead. I also thank my PhD students who have worked very hard for this course. And the last, I thank the participants. We have around more than 700 participants, not only from our country, worldwide. Thank you very much, and hope that you will get benefited. Over to you, Nadeem.
Thank you very much, sir. We straight away move to the next speaker, Professor F.A. Mir, sir, the Vice Chairman, IGS Chapter Srinagar, to please have his word on the STC. Professor F.A. Mir, sir. Please unmute yourself, sir. Sir, kindly unmute yourself.
Okay. Is it okay now?
Yes, sir.
Okay. Good morning, everybody. It's my pleasure and honor to welcome all the participants to this short-term course on advances in geotechnical engineering for sustainable development. Sustainable development is a present challenge to civil engineers, and for sustainable development, the part of geotechnical engineering need not be overemphasized. It's already there, and so would be the advances that come up along with that requirement. So I convey my appreciation and congratulations to the coordinator. My respects to our worthy director, Professor Rakesh Saigal, for encouraging such activities at the institute. Thanks to Professor M.F. Wani for collaborating through his TQ program with such activities, and all the more to all the participants who have taken time and taken efforts to register for this course and attend it. Now, this digital online interaction has become a requirement of present times due to the circumstances. We would have loved to have physical interactions at our institute, but in view of situation, we are forced to have such interactions. But this is very good that we are sharing our knowledge through these platforms, and this should certainly benefit all of us. I pray that we go smoothly through all these 5-day lectures and participants get benefited. They will certainly get benefited. I, on behalf of Indian Geotechnical Society Srinagar chapter, would invite all those participants who are based in Kashmir, Jammu Kashmir, Srinagar especially, that they come forward and join the Srinagar chapter, which has been established a long back, maybe around 20 years before. But many activities we could not take up except a few in the initial phase. And it was on the insistence of then President of Indian Geotechnical Society, one by the name of Mr. He was an MES engineer, General S.N. Mukherjee, that we established this chapter. And I convey my good wishes on behalf of my chairman of Srinagar chapter, Dr. Barakat Hussain, to all the organizers, and thanks and gratitude to NIT Srinagar for encouraging such activities. All the best. Good luck to everybody. Thank you very much for making me a part of this program. Good day.
Thank you very much, sir. We move on.
Welcome.
I feel privileged to invite the head Civil Engineering Department, Professor M.A. Engg, sir. Sir, are you there?
Am I audible?
Yes, sir, you are audible, sir.
Good morning, everybody. I would like to welcome all the participants to this online 5-day short-term course on advances in geotechnical engineering for sustainable development, being organized by Indian Geotechnical Society Srinagar chapter and Department of Civil Engineering, NIT Srinagar. I would like to offer my sincere gratitude to the patron of this short-term course, Professor Rakesh Sehgal, the Director of NIT Srinagar, co-patron Professor M.F. Wani, the coordinator TQP, Professor F.A. Mir, Vice Chairman, Indian Geotechnical Society Srinagar chapter. I would like to congratulate Professor B.A. Mir, the coordinator of this program, for having arranged this short-term course at short notice. Geotechnical engineering is one of the 4 major divisions of the Civil Engineering Department, NIT Srinagar, offering PG programs leading to award of MTech degree. The other 3 being the Water Resources Engineering, Structural Engineering, and Transportation Engineering and Planning. In addition to this, the Department of Civil Engineering offers undergraduate programs leading to award of BTech degree in Civil Engineering, and also the doctoral research program leading to the award of PhD degree. Geotechnical engineering encompasses the Can you hear me, please?
Yes, sir. You are audible, sir.
There have been advances in every field, and so in the field of geotechnical engineering, especially in the ground improvement techniques, soil structure interaction, geo-environmental engineering, and the development of softwares. I hope that the participants will get enlightened by the learned speakers. And in the end, I will quote the father of the soil mechanics, Carl Zagi. He writes, and I quote, Unfortunately, soils are made by nature and not by man, and the products of nature are always complex. With these words, I wish you a great week of enlightenment and learning ahead. Thank you.
Thank you very much, sir. The next speaker, we have the guest of honor, Professor G.A. Harman, sir. I respectfully request them to address the participants. Professor G.A. Harman, over to you, sir. Professor G.A. Harman. Sir, are you there? Harman, sir. Professor Harman, sir, kindly unmute yourself.
Hello, Harman sir. I think some mic issue is there because Harman sir has unmuted. Even then, we can't hear you, sir.
So can we move on to the next speaker? We have with us Professor M.F. Vani, sir, the coordinator TechCube 3. They are there with us. Sir, kindly one second.
तो શું કહેતા audio issue.
Hello.
Hello.
Yes, sir.
Hello.
Professor M.F. Vani. Yes, sir. Yes, sir. We can hear you, sir. Please continue, sir.
Good morning to everybody. Professor Rakesh Sahgal, Director NIT Srinagar. Professor J. Harman, Dean RNC. Professor M.A. Ahangar, Head Civil Engineering Department. Professor B.A. Mir, organizer of this course. Professor F.A. Mir, one of the senior persons working in the geotechnology in NIT Srinagar. Professor M.Y. Shah, another expert in the geotechnology in NIT Srinagar. Other participants, students, colleagues, and resource persons. I'm highly thankful to all the people they have given their time to be associated with this short-term course. It is good that the topic of this course has been chosen as the sustainability, which is one of my research areas, and I would like that this subject is taught in all engineering branches, including the civil engineering, in all streams like design, geotechnology, water resources, and the another is transportation. So this is the talk of the walk. We call it talk of the walk. The sustainability of the system, sustainability of the facility, sustainability of the structure, sustainability of mechanical, electronic systems, and all other systems which we are using in day-to-day life. I'm highly thankful to Professor B.A. Mir that he has taken the time and he has organized this course in civil engineering department, which is a very busy department otherwise. So I wish all the success, and I hope the outcome of this course will teach the people the sustainability, how to involve sustainability in our systems, how to design our sustainable systems for the future use. Because all designs which are not sustainable cannot sustain in the future, and all those designs will not be able to draw the attention of the people, and people will not use if they are not sustainable. So the sustainability codes have now come into existence, and they should be implemented in engineering, uh, all engineering fields of the engineering fields in everywhere. So especially in the case of buildings and big structures, sustainability has become very, very important. So I again express my gratitude and love to the Civil Engineering Department and Professor B.A. Mir and other colleagues which are with whom I have long association for more than 35 years. So our association has been big, and I hope this department will do a lot of good things in future also, as it has been doing in every walk of life in the state of Jammu and Kashmir, which is now Union Territory of Jammu and Kashmir. I am thankful to you for giving me time to speak for a few minutes. Thank you very much, and I wish all the success for this STP.
Thank you very much, sir. Thank you very much. We have with us now our guest of honor, Professor G.A. Harman, Dean Research and Consultancy. We request them to kindly address the participants. Professor G.A. Harman, sir. Harman, sir. Sir, you are unmuted, but we are still not able to hear you. Harman, sir, are you there? All right. There seems to be some technical issue.
He can address us via phone.
Hello, Nadeem. Nadeem. Hello? Nadeem. Hello. Are you there, Nadeem?
No, question of speaker. Sir, can you give us
Professor D. Mees, coordinator of the program, Professor M. F. Wani, teacher coordinator 3, Professor F. A. Mead, Vice Chairman, IGS Srinagar chapter, dear participants and colleagues, it gives me immense pleasure that civil engineering department is currently organizing a course on the geotechnical aspects and the sustainable development. And it is indeed the requirement of the time, and the e-mode is the only mode under the COVID conditions that exist. Therefore, it is indeed giving the chance to the participants to know about the activities in the field and how yesterday's technologies have become obsolete and today's technologies will be uncertain for tomorrow, as Professor D.M.E. rightly pointed out. I find that the importance of such a program is so much required for our place in terms of the practical problems that we are facing due to problems of soil and the related aspects. That, for example, the drinking water supply to the Srinagar city got affected recently due to the instability of the slope near Gandharval, hill. Basically, they are trying to build a bridge, however, the instability of the slope is giving problems continuously. And this problem has not been addressed, and our Department of Civil Engineering has got responsibility in terms of its geotechnical section that they come up with a long-lasting solution for such a problem. Moreover, the other problems which are there due to instability of the slope on the highway from Jammu to Srinagar, you will find that the host of problems which have been created by blasting of mountains, which are geologically young mountains of the Himalayan range, and these present formidable problems for our budding engineers as well. The civil engineering department has taken a lead in terms of addressing some of these problems. However, now another dimension, which is sustainability, is attached to it. I know that Professor Dagg's, approach has been, a kind of a cornerstone for modern developments in the area, and grouting technology has now come to a stage while grouting technology manuals are available. It is not just drilling and grouting only, the permeabilities and related aspects of this particular branch of engineering are indeed challenging and formidable. I know that the area deals with legions and copper legion and stuff like that. So apparent legion theory, which is so much used by the people, and they are taking risks and they call them novelty risks. And the uncertainty in the future is to some extent, taken care of. However, in situations like dams, where cut-off walls for dams are used for repairing of foundations, the hydraulic distress which develops, unfortunately, which can lead to muddy flows and erosion and other aspects which are very much akin to this branch of engineering. The distress in dams in particular is a challenging problem southward, and such a program will give an opportunity for the participants of our country and abroad to know about how people are taking different, strides in this particular field of engineering. there is also the problem of erosion, which is deeply connected with this particular branch of engineering. We therefore have got such solutions as composite wall solutions and other things which are coming up for sustainable development. Now, to say a few more words that the particular, course will address these kinds of issues probably. But one important point I want to make is that the contractor of the civil engineering problems is not generally related to how the engineering will take its stride. However, this particular branch requires the contractor's role as well, and it cannot be set aside. Many strikes which have occurred in this branch of engineering have been through active participation of contractors as well. Finally, I must congratulate the Civil Engineering Department for having organized this course. I congratulate the head of the department, Professor Engg, Professor D.A. Mir, Professor F.A. Mir, and Professor N.F. Gwani for having taken this kind of an initiative and helping the participants in these tough COVID times. Thank you very much. I wish all the participants an enriching experience in this particular course. Thank you very much.
Thank you. Thank you very much, sir. We regret the delay that was caused due to some technical issues. Moreover, we are unfortunate in the sense that we could not get in touch with worthy director, also the chief guest of this STC, Professor Dr. Rakesh Sehgal, sir. So we move on. We have with us the senior faculty of geotechnical engineering, Professor M.Y. Shah, sir. They kindly express the vote of thanks. Professor M.Y. Shah, sir. Sir, please unmute yourself.
Am I audible now?
Yes.
Okay.
Go ahead.
Yes, sir, you are audible.
Respected professors, Professor M. Afwani, Professor J.
Professor
Harman,
M.Y. Shah, sir.
Professor Fayaz Ahmad Mir, my senior teacher, and all other my colleagues, participants, and learned speakers. I would like to present my vote of thanks to all of the people who have initiated this course and our worthy director who have encouraged it to go for the course, because this is increasing the you can say the credibility of our institute, and these courses we must now help in off and on. And our professor M.A. Ahangar, our HOD, has been very kind to approve this course and allow the department to conduct it. And Professor Rakesh Sehgal, the director at I.I.T, is kind enough to allow this course to happen. And Professor Afwani is also thanked for having a financial support from the TCube. I would like to thank particularly Professor B.A. Mir for taking the initiative and working very hard towards the accomplishment of this course. I congratulate my research scholars also and all the research scholars of geotechnical section that they have worked hard for the conduct of this course, and I welcome and thank all the participants also. I also thank all the learned speakers who have agreed to share their experiences for at a very short notice. Okay. And I would like that during this course, every participant will take maximum advantage from the learnings of their learned speakers and help us in conducting the courses in by giving the feedback as well as the loops and loopholes which will be maybe coming in the coming days, so that we can improve in the near future. I lastly thank all the people involved in this course, and particularly the director, Professor B. A. Mir, Professor M. F. Wani, Professor G. Harman, and all the people. Once again, I thank you for the support and conduct of this course. Very much thank you. Over to you, Nadeem.
Sir, kindly mute yourself. Thank you very much, sir. So we are now moving on to our technical session. We have with us Professor Ashish Juneja, sir. So I would request Professor B. A. Mir, sir, to introduce Professor Juneja, sir. And coincidentally, he has been the supervisor of Professor B. A. Mir, sir, in his PhD doctorate work. So we request Professor B. A. Mir, sir, to introduce to us our eminent speaker, Professor Ashish Juneja, sir, from IIT Bombay. Over to you, Professor B. A. Mir, sir.
Thank you, Nitin. Good morning to all, and I am very much pleased to introduce my guru, my teacher, my advisor, because of whom I am here now, and what I do because of his all efforts during my doctorate work. Dr. Ashish Juneja is professor at IIT Bombay. He earned his doctorate from NUS, National University Singapore, in 2002. He holds his master's degree from IIT Delhi and bachelor's degree from University of Roorkee, now IIT Roorkee. Professor Juneja worked intermittently in the industry for about 8 years in India and abroad before returning to the academia in 2005. His research interests are in dynamic soil behavior, numerical and physical modeling of underground structures, and ground improvement works. He has supervised 1 postdoctoral and 8 doctoral students, and I am the first among them. I am very happy to be, and is presently guiding 4 doctoral students for their PhD. He has also supervised over 15 master's dissertations at IIT Bombay. He has co-authored over 80 journal and conference publications and 2 book chapters. Professor Juneja has received research grant from DST, Ministry of Earth Science, DRTO, Railways, and number of other public and private organizations. He also serves as a consultant to various government agencies, national and international organizations such as Railways, NPCIL, Mumbai Metro, Nagpur Metro, BMC, Samsung Engineering, Jan Delnal, and John Deere. He is a nominated member of TC104, Physical Modeling in Geotechnique, and TC204, Underground Construction. He has organized many training programs and workshops at his institute. Professor Juneja's teaching performance has consistently been evaluated as one of the best teachers, has been teaching core subjects in geotechnical engineering at the undergraduate level and subjects on constructive models and ground improvement at postgraduate levels. Some of his popular courses have been transmitted live through ISRO satellite to remote centers and other engineering colleges across India. In recognition of his outstanding contributions to teaching and research, he received the Excellence in Teaching Award twice in 2012 and 2016 at IIT Bombay, Industrial Impact Award 2014, and Best Paper Awards. Professor Juneja is a very hardworking professor and well-time management. During my course over there, I learned many things out of him. And whatever I do today, whatever I pass on to my students, it is because of Professor Juneja. And being very busy in his schedule, when I requested him, at once he accepted my request. Sir, I am very much thankful to you and sparing precious time for this course. Thank you, sir. Floor is yours.
Thank you, Professor Mir. It's an honor to be present in front of so many distinguished people, and I'm really grateful for you to invite me today. So, in fact, when Professor Mir introduced, some of the awards were thanks to him. In fact, it is he who has helped in getting those, at least the best paper award. I remember goes to his contribution. Okay, so if you allow me, can you please allow me to share my screen? I can then open up my presentation.
Yes, sir. Yes, sir. Just a moment. Just a moment, sir. सर बोल रहे हैं Sir, please check it. Yes, sir. No,
Okay, thank you. So my presentation today is in fact on a genesis of this work is from an idea that, quite a number of foundations in this country are, especially embankments, railway embankments and number of bridge embankments, they're over 50 years, 60 years, and even longer. Some of them even have crossed centuries, a century, and they have we are unable to replace those foundations because of the nature of their lifetime. But what we can do is to look at the whether we can retrofit the foundation. So that is as part of superstructure. But having retrofitted the superstructure, what about the foundation? You cannot simply excavate the ground and do something about it. So what best can we do with the existing foundation, and over the life period of so many years have passed, whether the foundation or the bearing capacity of the soil has improved over this period? We are very well aware because of the number of cyclic loads. For example, in this photograph over here, it shows an embankment, simple railway embankment on which probably daily you have hundreds of trains passing through. And so over a period of decades, whether we do see any change in the bearing capacity of the soil. A simple case can be because if you recall about, I think about 2 decades back when railways started to, enhance the axle load of the goods train. So there was a sudden increase by 10 to 15% increase in the axle load. So whether with the new axle load, are we able to get the required bearing capacity? So over here, this work I intend to present is of Dr. Muhammad Aslam. It's his PhD work, which he recently completed about 2 years back in IIT Bombay. So the entire presentation, I think I'll have to show Thanks to him, because it's his effort that the data and the analysis has been done. Right. So let me start by showing you a very simple case of uniaxial loading of a few material, just to give you a background of what the intention of this presentation is about. So if you look at the first top left figure, you see a stress strain curve of mild steel. It's a simple case wherein which probably many people, even in their first year of engineering, many students would have conducted such a test, wherein you have a linear elastic material up to a point. So that's the yield point we define. And if we unload below the yield point, the material behavior is elastic. But beyond the yield point, you do get some plasticity coming in. Okay, plasticity meaning if I unload, there would be still some amount of strains which you can't recover. A second case is your elastic rubber. Non-linear elastic would be a case of, where you loading and unloading follow a different path. So that's the second curve over here, but you do get full recovery. The third one is perfectly plastic, which is an idealized material not really existing in practice, where the material deforms without any strain and it just fails. A brittle is a glass, and elastic, perfectly plastic down bottom is a friendly more Coulomb stress strain curve. But what you would be interested to know is the bottom right figure, which shows the work hardening material and work softening material. These are the kind of material which represent our day-to-day soil. So soils can either work harden, soften. If you compare this curve to the remaining curves, you will find that none of the remaining curves you are able to match with them. There is definitely something wrong with our, at least, I won't say wrong, but there is the assumptions made are pretty much different than what real soil is. So to conclude from this slide, important conclusion is soil is highly nonlinear and it's plastic. So any point you unload, you do get some plasticity set in. So nonlinear plastic. So is there any other thing which we should be aware of? So in usual case, if you look at the figure on your right, I think it's good idea to start from figure on the right, wherein you have 2 points A and B. They represent the soil state on either side of the failure line. Your CSL is a just for the time we look at CSL as a failure line. So the soil both A and B will have a tendency to move towards the failure line if they are tested, if you apply certain additional load to it. What is important is both the soils have similar void ratio. They both lie on the same horizontal line, but they move in different direction. So one important conclusion is the direction movement is because of, if you look at the horizontal axis, it's stress, mean stress. So whatever is the starting mean stress of A and B is different, but void ratio is the same. So can I now say, without even looking at the left-hand side figure, which is your standard triaxial test figure of those A and B samples, they both have same void ratio, but they move differently. So can I say that yes, soils are nonlinear, plastic, but also stress dependent? So these three are important. If you intend to use a soil in your your analysis or in your design. So with these three unknowns, what are the assumptions we make? So those are for maybe a single stress strain load, wherein you don't have any multitude or load cycles coming in. So what about if you have a single load unload cycle? So that's the top left figure over here. It's in fact a standard odometer test. Many of you would have an experience in laboratory experience in doing a consolidation test, where you move along you plot E void ratio versus effective stress, and you move along the normal compression line, and somewhere over here you decide to unload. So I think I can even use a highlighter. Just a second. Yeah. Yeah, this seems better. So you stop somewhere here, and then if you unload and you reload, you do get a loop or hysteresis. but the assumption made, which is on the right hand side, is that the unloading, reloading is the same track. So this is one important assumption which in fact simplifies our life a lot. So if I go down to the bottom figure, the same figure, now what we are showing is the unloading, reloading is, if I do even once, twice, hundreds of times, millions of times, the path is the same. So the final point after reloading, it still comes back to the same point B. Okay, this is the limitation of our work, meaning if I have hundreds of cycles of loading, my soil behavior will not change even if it is after a single cycle or even if it's a million cycles. But this was the case for drain. So this left hand side is the drain test, but I can draw similar conclusion if I speak about the figure on the right, which is the undrained test. So undrained test is similar. I have a path which moved from A to B. Just try to visualize this is your undrained path. And B, if I decide to unload, and unloading comes back to C. If you recall, C and A have the same deviator stress, where Q is your deviator stress. So I have reached to C and it's the same deviator stress. Obviously, horizontal stresses are effective. So effectives will be changed because in undrained, you have some amount of pore pressure which is locked in. Okay. So the idea is that the path still goes up and down, even in undrained. So you can't use the conventional theory, whether you're, you're working on your, what do you call it? You know, critical state, more Coulomb, any theory you are using, you are used to use. You cannot use those concepts in multi-tool loading unless you make some assumptions. So today's presentation will be on some of these assumptions which we have worked on. So this is a real problem which it shows a time graph series where I think if you look at it, the bluish color is your load. So you have one sets of cyclic loading, then followed by a static case. Maybe a train came in again, a second set of cyclic loading, then no load, then a third set, and blah, blah, blah. The reddish color which you see is the pore pressure which is generated. So the excess pore pressure due to the first cycle, the next set of cycles, I shouldn't say cycle, but set of cycles and so on, the pore pressure generated each time is less. Okay, so it's a real problem which you cannot use the conventional theory to solve. So in other words, just to point this out, your stiffness of the soil usually will decrease at the end of each cycle of load. Okay, stiffness decreases because pore pressure is built up, and in between the cyclic loadings you can have drainage occurring, because of which the pore pressure decreases. And the last, of course, we can't touch it in usual day-to-day life, because even in if you look at the most advanced research problems which they solve, it's quite difficult to solve a complex problem wherein the soil is draining at the same time it is being loaded. Okay, such a problem is highly complex. So when the soil is subjected to a certain cyclic loading, okay, these are three important conclusions, or I would say what happens to soil if certain cyclic loading is done. And it's a very standard, if you open up a standard textbook, these are probably the first 3 lines written on any standard dynamic testing book. You can have either a flow type failure where the material just a loose material or soft material, just after going a number of cycles, usually a less number of cycles, it just loosens up, it just fails, so it just softens, it flows, starts to flow, it liquefies. A cyclic mobility is usually for dense or stiff, meaning you do see a lot of resistance to failure. But since after certain resistance, there is a drastic, deformation. So these are the stiff or the dense soils, and you see some stress reversal occurring in them. The last is the, what we are more, like for example, if you have an embankment, a compacted embankment, things like that, where certain degree of engineering has been used to, make the material slightly firm. So these are the plastics where you see some plastic strain accumulation, meaning over period, a certain amount of, either if you're doing axial loading, in a sense it's a K-naught condition, or any kind of accumulation does occur. So these are the three deformations which with this, we are normally, looking into. So my presentation will all, in next maybe, so 50 minutes or maybe an hour, we'll just move around in this direction, that certain points we will look up. First of all, we will try to measure the stress, pore pressure. What are the measurements made due to cyclic loading? So these are very simple laboratory tests which we have conducted from a few cycles to over 1,000,000 cycles. So million means the test would have gone up to really close to a month or so. So running a month-long test. We kind of looked at certain degradation model. So because of pore pressure accumulation, what kind of, how the soil gets degraded, and maybe these models or this talk on second point will give some of you certain idea, a research idea, wherein you can give a thought to know whether it is applicable to your maybe day-to-day problem. The third one was just a trial basis, which we did on intermediate drainage. And I'll just give you an answer to the third. We says even if you stop in between and do a cyclic loading after some time, it is the same as doing a single cyclic loading to the end. So I've given you the answer for the third bullet, which I'll just briefly show you. And we did say that what happens to the soil structure. So because of all this cyclic loading, so all the soil structure measurement we did not do, because the structure measurement was not part of this entire work. But the answers we got from the remaining test, they helped us to reach to this conclusion that the soil structure would have been disturbed. So these are the three different soils which we used. We kind of started with two of these sands were from I think close to the state where a lot of liquefaction occurred in the state of Gujarat. The third one is close to the northern part of India, wherein a lot of silt was collected. So you have two sand samples and one silty kind of deposit. I think silt had some plasticity, if I recall. I can't remember. Yes, it has some plasticity, but it's too low to really take advantage of this plasticity. But all the three materials lie, if you look at the top left grain size distribution curve, they lie within the somewhat liquefiable soils, which are the range which is defined for liquefiable soils. So they were conducted in using our cyclic triaxial equipment. This is a photograph of part of the photograph of our lab. If you do happen to visit us, please come to our lab. We will be glad to show you around. We have invested a lot of on dynamic testing. So we have cyclic cyclic triaxial, cyclic simple shear, resonant column, Bender elements. So all these are related to, of course, dynamic, to evaluate dynamic properties. The figures on the right show you the sequence of sample preparation. We used 100 mm diameter and 200 mm long samples. So these three kind of soils gave us a complete scenario of what kind of failure planes are you can visualize. So if you have some soil mechanics background, the left hand side figure, top left, you can see is a shear plane, clear shear plane has been formed. You can in fact measure the angle alpha. And if you are aware, alpha is 45° plus 5/2. Simple soil mechanics problem. Yes, I think this was not so funny, but bulging failure is something which probably is where the material bulges, becomes fat at the middle. It's more like plastic deformation. And the right hand side shows all the stress strain curves, which for different OCR values. So we made samples, loaded them, unloaded them. I don't want to discuss these stress strain curves. They're typical, where I think any standard lab will be able to show you. Now, this is one important slide which I would like to highlight. It is if you're working on granular deposits, you would be aware that granular deposits, there's few methods of sample preparation. You can do pluvation, you can do tamping, either dry pluvation, wet pluvation, dry tamping, wet tamping, and of course there are all kind of different things. So if you look at the results, okay, this is interesting. No matter what method you use for pluvation, okay, whatever method you use for sample preparation, the end state, the final, when the sample fails, is the same. So I have prepared a sample using different method, but the ending, the sample will fail at the same failure line. The failure surface will be the same. This is again an important conclusion, but it has a strong but, which is on the next slide. The but is under cyclic loading. Obviously, we are saying that the ending is the same, but if you look at the two curves, bottom figures, the left and the right, I would not go much into the data point, but if you look at the band, the slight difference in the trend, you see that if the left hand side figure, if it's pluviated sample, and the right hand side are the results of sample test results on samples prepared using tamping, you do see that although the ending is the same, but the number of cycles to reach the ending is different. So if you prepared a sample using a slightly different method, you may get an answer that the soil will liquefy or not liquefy based on the method you have prepared for sample preparation. So this is a word of caution which you should have whenever you discuss dynamic testing, laboratory sample preparation, that when you speak about liquefaction, that unique number, when you say my cycles, my soil liquefies at 8 cycles, as in our Indian standard procedure which we follow in the liquefaction design. They just say that if n is certain value, you look at what is the n value for an earthquake of so and so magnitude. That n value is highly dependent on how you have prepared the sample. This is the, of course, conclusion of this slide, which you should be careful of. So we did the same, testing of, cyclic loading of all the three kind of samples. These are three, I think, just three examples of three samples. But if I recall, I think close to 40 plus, or maybe, I can't give the immediately plug the number out, but I think close to 40 or 45 tests is what, Aslam did manage to do. So he really worked quite hard. Doing a single test is not easy, I'll tell you. It's a painful thing because every test you can't get a success. You need to really be, it's a patient job. Of course, people who are doing laboratory testing, they would understand that the preparation of sample can take days, but testing can be just, a moment. It could be just a matter of few hours or few minutes that your test is over. So that's again, I do appreciate the work done. So if you look at the plot of excess pore pressure ratio, so it's just, like whatever is the pore pressure developed due to cycle divided by the initial mean effective stress. So that's how RU, which is the vertical axis, defined. So when RU reaches 1, it's in fact failure. Your soil has failed, or I would say it's close to 1, it has failed. Why 1? It's just close to 1. And horizontal axis is the number of cycles to reach failure. So these are again you could say it's a log scale. It's a huge number. And if you look at these curves with the the lower the stress amplitude, so 0.025, and is an example, is what is the a load applied. So normalized load, we normally speak in terms of cyclic stress ratio. So how much of load you have applied over divided by the mean initial effective stress. So again, take these numbers for the time being, that these are the numbers which you have applied. Okay, so a smaller the number, you do expect that the soil will be able to take a lot of loads, and bigger the number over here, for example, 0.125 is a number where the soil will fail within a few cycles, maybe 3, 4, or maybe 10, within 10 cycles as shown over here. So this number is where we got it varied, and it all depends upon what kind of loading you're looking at. So if you're looking at a case where you have railway loading or an earthquake loading, an embankment loading due to heavy trucks going in. So you can safely say this entire range covers the range which all dynamic loads you can think about. Okay, so different models do exist for wherein you are you can model. Different models do exist wherein you can see or I could say wherein you can use them to predict what are the, first of all, pore pressures developed, the strains which will develop in the soil, and likewise the stresses, the change in stresses will occur. So these cyclic models can be grouped into either empirical, so they are based on laboratory test results. Empirical is quite straightforward, that you look at the results and you try to retrace the curve using some kind of statistical tool. So either that's how empirical works. And a constitutive should be, in fact I should have put in a horizontal line over here, because all these constitutive relations are, they take the input from the empirical, so they do take laboratory input. So they should have an arrow over here, so I'll try to correct it next time. But these constitutive relationships can be based on they're based on elastoplastic model, meaning they do take into account the soil, what kind of soil exists. So rather than just look at the results and use some statistical tool to retrace the path, you do look at what soil, what is the property of the soil. This is important because then you can not only say that, for example, if I use a different soil or the same soil under different loading condition, and you get a different, of course, different results from different statistical tool. So if I use the left hand side and I change the loading condition, I'll get a different result. And then I'll have to go back to my table again to use a new kind of develop a new kind of tool. In other words, I won't be able to explain how the soil behavior, why the soil has behaved in that manner with the change in loading condition. This is what the right hand side answers give. So our focus was to look at the right hand side, but I will briefly touch upon the left hand side as well. Okay. So a very simple case, if you have looked at some simple modeling, is an equation given by, I think this is a very common expression where n is the number of cycles to load. I'm not sure if I should have called it Z. I think this is called as Z. So Z is let's call it as an adjustment factor. It tries to adjust the development of pore pressure with cycle loads. Okay, so this is how a very simple model would be. So if you look at the figure at the bottom, okay, so I think if someone can stop doing the annotation, you are doing, and I will not be able to stop the annotation. Thank you. So the number of the number of cycles to failure is the left hand side, and horizontal is the factor is the again Z. Okay, what you see is the data you can fit the data up to a certain number. So I'll just look at the number of cycles wherein this particular method can be suitable in the next slide. But what you see is that even with a simple tool, you can fit in data. It is not that you need a complex procedure or complex method to solve a problem. Simple tools can help. So with these simple tools, let's look at some of the results. So wherever you see a curve with some symbol, so these curves with symbol are our laboratory data. Okay, these are all laboratory data, curves with symbol. A continuous line is the prediction. So that's the prediction which we have, continuous line. What you see is for small cycles, maybe up to 100 cycles or so, the prediction is not so bad. Even up to less than 100, the prediction is really not so bad, I would say, but not always. In some cases, but a large cycle, yes. So large cycle, when you cross, the prediction is actually goes haywire. It just tries to miss the final value. So even in small cycles, you are able to get some prediction, for example, in this figure, but you do see, so give me a second, please. I'll have to close this just 1 second because I'm using a phone and it's being causing some disturbance. Just let's see. Yeah. So I hope, okay, so I'm back. So yeah, sorry for that. So now, yeah, it's just that my camera on my laptop is not working, so I've just connected a camera using mobile phone. So the phone may ring in between, and so I've tried to put it in different flight mode. Sorry for that. Okay, so what it shows is even the prediction. Yes, you can get reasonable prediction, but not always. So that's the case. Not always is something which you can get it. So let's look at some other procedures which have been used. So this slide will show you the power, the power power models which have been used. It's like putting y equal to x to the power of something, a simple mathematical tool just to curve fit the data. Okay, so what you see is the number of cycles, see, yes, the power model does help. If you look at it, it does help, but not always again. Especially, if you're looking at the curves which are for, which start off slowly. So the power model has a limitation. It starts off pretty fast. The beginning is fast, but then it tapers off towards the end. So that is a limitation of power. It's it just picks up pretty fast. So the right hand side figures, of course, with the different soil type, you can get we said y equal to x to the power of something. So those powers you can get based on laboratory data, and it's not difficult to get those numbers for your soil. And for my soil, it's this number. Maybe for your soil, it could be a different number. So you got to be careful on this when you use it. When you use power model, somebody else power model for your case. So you got to be careful because those numbers are built for that particular research group's problem. And there is another set of model which is based on hyperbolic. Again, like I said, it's a curve fit model. Hyperbolic. Again, hyperbolic has again another drawback. You remember we said power, it picks up very fast, but later it's smaller. Hyperbolic is just the reverse. It picks up slowly. So you look at the data, broken dots, it's slow to pick up, but later it starts to pick up pretty fast, I would say. But still, even for a large number of cycles, you do get, especially somewhere here, you do get not a nice fit. Plus, it won't tell you anything about volume change. It won't tell you anything about the soil behavior. It just tells you, yes, you are able to fit the data. And this is how many research people do get away with, just by curve fitting the data. They say that this is an answer, which I can say maybe we can do slightly better than that. So with this betterment, I think we looked at how do we bring in a simple constitutive model, into our, this scenario. So if you look at, if you have, looked at something like a, critical state soil mechanics, you would look at, if I show you this kind of hump thing, it won't surprise you. So in critical state soil mechanics, there's one big issue over here. So let me just look at the left-hand side figure. In critical state soil mechanics, again, if I load to this thing to one point, okay, and unload it and reload it, and I do this millions and zillions of times, hundreds of times, unlimited times, the path just goes up and down. It just retraces its path. I'm not able to, do the accumulation of pore pressure, accumulation of strain, because the path does not move towards the Q axis. So if you recall in your basic soil mechanics, if I move towards the Q axis, I'm actually moving towards failure. So I visualize that, I have not drawn, but visualize that there is a failure envelope over here, somewhere here. Just visualize this, please. So the path is tries to move towards the failure envelope. That is the objective. When I do multiple cycle loads, it should move towards the failure envelope, which unfortunately a simple constitutive model, because of its assumption, cannot do it. So what we did was use this simple model. So I will not disturb you by showing you equations over here, but just ignore left and right hand side. Just look at this theta value. If theta, just look at theta, and if I say theta equals to 1 or theta equal to 0, so this is the range we can adjust. So in the usual case, if theta equals to 1, this path will just move up and down, right? And if I adjust this between 0 and 1, what you see is the path. So that's the path. It moves not only up and down, but it moves left towards this line. You see this line towards the failure axis. So this part has been just zoomed in. It's the same. It just shows that every time you load and you unload and reload, the path starts to move towards the left. It's because of this theta adjustment. So with this adjustment, what you do is you not only use the soil property. So you're not really looking at the result and giving a curve fit by just using a statistical tool, but all this, each and every curve, what you have developed is based on some soil property. So you use or you justify the use of a particular soil to reach failure. All right. So this is the range. For example, yes, this is, I've just said, if theta equal to 0, it's your ordinary, unload reload where there is the path retraces, and if you put theta equal to 1, then the path starts to move towards the left. So this is the range we have just said. So I'm just going to sorry, skip this slide. I'm sorry for these equations. I will not again go through these equations, but the procedure to solve this model is available in one of the papers. So if you have bottom right, it was published in Journal of Earthquake and Tsunami quite recently. So I think you can, if you would like to do some algebra, if you're keen to do some mathematics, you're most welcome to refer to this paper for how we came to reach this the final theta value and how we use the theta value in the soil model. Okay, so having developed this theta, let's see what are the different curves, different results. Okay, so what we see is, despite doing all those effort, my theta, which is shown by broken line, incidentally, this theta is based on original Carter's model. So the Carter et al., they developed a model for clay, and we kind of adapted it for with certain changes, we adapted it for our sand and silt. So of course, Carter's model has a limitation. So with these limitations, let me say, we try to highlight the limitation of Carter's model using our results. The limitation are quite clear in front of you. None of the broken lines, you see the broken or the dashed lines, none of these lines you are able to follow using the continuous curve. The continuous curve and the broken lines, they don't match. So Carter et al., they gave a fixed value of theta. They said, for their clay, they used a theta of something, I think 0.1, if I remember, I vaguely remember. But our theta, you see here on the right-hand side, 0.1 did not work for us. We used a range of theta varying from, close to 0, going right up to close to 1. So our theta did vary. So none of these theta, even by varying the theta, we would say the Carter et al.'s model worked, okay, even with modification. The second thing which I think is important conclusion is, which was not highlighted earlier, is this theta depends upon how much of stress you have applied, how much of what is the cyclic load you have applied, the CSR. So that is the loading you have applied, right? We said normalized loading by divided by the initial mean effective stress. So it is dependent upon the load, the magnitude of the load, which was surprising, which in fact was not highlighted earlier. And for our soils, we could see no matter you use for our different soils, it did not matter much on the kind of soil for the theta value. So although it's different than the earlier clays which were used, but it did not matter much for our sand and silt. So we did some adjustment to it. We got in whether we can adjust the theta in terms of number of cyclic loadings. So we got in n, of course. So if you are at the maybe at 1000 cycle or 1005 cycle, so your theta will be dependent. Obviously, the more the cycle, the more the model has been degraded. So this is what we did. We went back into the soil model. We used the readjusted, I would say, we engineers like to call it readjusted, but to be honest, it's just fudged value. You have just, because you want to match your results, you have fudged the theta value. But before I continue or say anything more, if you compare this model to rather some of the complex models, for example, in case you're working on dynamic testing, you would have heard of PM4 sand, UBC sand. All these models require rather complex testing and a lot of input parameters. So compared to those models, I would say this is a much simpler model, although it requires a bit of mathematics, but still, nonetheless, it's still simpler than the those other complex other constitutive models. So, yeah. So we have over here with this adjustment. Now, what is surprise to us? Yes, you do get some better fit close to earlier part, and even for small number of cycles, say close to 100 or so. Okay, over here it's not a good match, but you do get some kind of better matching. But obviously, when the number of cycles are large, maybe they exceed 100, then the match goes haywire. It actually, you're not able to get a good match anymore. Okay, so there is some betterment with this use of theta, but nonetheless, it's not the perfect. You do need some other adjustment. But what is surprising is obviously for the three soils, this time I think this is again another the Xi thing, Z or Xi. I'm not sure whether what should I be calling it, but you see that this value is affected by CSR, but it is not dependent on the soil type. Okay, so what we thought of doing was look at the the stress plot. So the stress stress plot, in fact, gives a much better picture compared to, the previous plots. Why I say this, let's look at the left-hand side figure of, the stress plot over here. What you see is for the, let me just go back. BS sand, which it says is more like rounded. Okay, BS sand is rounded. Silt and GS sand is angular. So this is again, we are going into some kind of structural behavior of the soil. What you see is the rounded, rounded particles, they do develop some kind of different behavior compared to the angular one. That is one difference. The second one, that is the number of cycles leading to failure. The second one is the phase transformation. So the limitation, despite all that adjustment, you are not able to look at the phase transformation. When I say phase transformation, this is again an important thing. You will probably find in some rare textbook that when the soil reaches failure, so very close to the failure, that means the last few cycles, when the soil has almost reached God, it's reaching God. You see a lot of unevenness, a lot of changes occurring. So the last few cycles are where we can say there is a transformation from contractive, because the curves are going in this manner, the bending away from the vertical axis to the right hand side, so bending towards the vertical axis. So we call this as a phase transformation, where the bending changes. It becomes from a contractive to it becomes dilative behavior. So this phase transformation, despite all this adjustment, you can't do. This is a major limitation. The second is, of course, for the the angular particles, which is on your right hand side, you will find that the pickup is much better. So if you look at it, the cycles, the loops, they become flatter. If you look at it, the loops, the loop is more vertical, but later it becomes flatter. So this is the starting point, and the ending point is over here. Similarly, the starting point is here and it moves towards the left. So you will find that the loops become flatter. You are able to predict the flatness for the angular particles. So GS is angular, HS is angular. Some kind of flatness you can predict. I don't have the figure for BS. I think it should have been there. But BS, the flatness, you are not able to predict much. Okay. This was one major another major difference. So we looked at the comparison with literature. So despite all this, literature does give a good comparison with the output. So that was one. And the long-term behavior was rather strange. If you look at the long-term behavior, you'll find the pore pressure with number of cycles going up to millions of cycles. It's still it does not pick up, and the prediction will not be able to do this. Will not be able to predict the long-term loading behavior. So there was another. So there it means you need to bring a phase where the short-term behavior is, or a short number of cycles is distinguished from the large number of cycles, and this change occurs at about, if you look at some historical data, in about 10,000 cycles. So if your number of loading cycles are less than 10,000, you have a different soil behavior. More than 10,000, your soil behavior is slightly different. Okay. So with this knowledge, we said, and a lot of researchers have come to different numbers. So our idealistic number was around 10,000. With this, finally we could get a better match. Again, when you say better match in experimental data, it is never perfect. If you achieve, I think somebody this morning said, quoted Tazargi, that Tazargi said that soils are deposited by nature, and you can't really do much about it. It's true. You can't play with nature. So whatever the nature tries to tell you, you have to accept it. This is rather interesting plot which shows how the different curves develop. And I'll just show you the first one over here. Please do not look at the remaining three. The continuous, I think, bluish line are the statistical tools which are used. Remember, it doesn't go up and down. The cyclic loading you can't predict. You're only looking at maybe the topmost point or somewhere close to the top. Statistical tool you can't predict. Your experimental result is something, I think it's a reddish color. It goes up and down, and our current research also shows up and down. We can do up and down with our current research. You'll see the blackish one which goes up is our current research, and I think the reddish one I can't see very much on the small screen, but we are closely able to follow whatever the data tries to tell us. So this is, again, I would say, a good part of the conclusion. There's one small work, if you permit. I just will take another 10 minutes to conclude this work. So after cyclic lowering, we decided to drain the water out. So it's so you allow volume changes to occur, and then do a static load over it. So you're looking at the post. I shouldn't use the word post liquefaction, because majority of our samples, or maybe I would say more than half of the samples, did not liquefy. So we are looking at a plot. So vertical axis, if you see, is the pore pressure ratio. We did discuss that anything above maybe 0.9 is something which the samples have liquefied. Okay, so point A, we are still slightly less than liquefaction, but there are data over here which have liquefied. And you have samples wherein the excess pore pressure ratio is too small, despite doing a number of cyclic loadings. So depending upon how much the pore pressure developed, you have the post-cyclic volumetric strain. So how much of water has come out of the system, you just calculate your volumetric strain. So if you are keen, I'll discuss this, but this work has recently been published in another paper of co-authored by Aslam. So if you again, this is interesting. If you are in, if you're looking at loading, unloading. So this is again this curve over here. The left-hand side shows the plot of. It's a void ratio. Specific volume is a void ratio, and your horizontal axis is a mean effective stress. It's an odometer consolidation plot, which you do in your lab. What you see is samples in which your excess pore pressure ratio was less than 0.75 is shown by continuous arrows. So the continuous arrows are more flatter. If you look at them, they're just almost flat. Okay. In fact, the flatness follows the in odometer or consolidation. You would have studied recompression. Those who are familiar with soil mechanics would be familiar with recompression index, or I think CC, CR, or some textbooks they call it as reconsolidation, something like that. So this is our continuous line. So continuous line, you'll find they're all parallel, and they follow the same slope as the original recompression index. This is interesting. Whereas the broken lines are the one where pore pressure was large enough, more than 0.75. What you see is there is a change in recompression index. Oh, this is surprising. You would not expect this in conventional soil mechanics, that due to loading, unloading, your CR or recompression index changes. So our CR is represented in terms of kappa. Okay, this is again a symbol which we use. If you go to certain advanced soil mechanics, it's slightly different than C recompression, but those who are familiar with recompression can easily correlate to this kappa. So kappa naught is the original slope, whereas kappa dash is the new slope. So what you see is this K star or kappa star is not equal to 1. It should, it should have been 1 as per our standard soil mechanics teaching, or what we have been taught or what we have been teaching in our undergraduate school level. But it's different, and in terms of soil which we have studied, it has a range of above 2 and close to 4. So it has a range. Kappa has increased due to cyclic loading. Okay, this is one good important conclusion. These are again standard stress strain curves for post-cyclic. So you have allowed the pore pressure to dissipate, and after the dissipation, you do a conventional triaxial test. So the black color curve is the original sample. If there is no cyclic loading, no pore pressure development during cyclic loading, and all the colored curves are the ones which are after the cyclic loading. Now, I'm not going to go into each and every specific curve, but if you look at the trend, irrespective of whether the pore pressure which was developed is less than 0.75 or more than 0.75, you do get a strength increase. Okay, so we one look at the curve, you would have thought, at least those samples wherein the volume change was less. So if I just go back, yeah, this curve, wherein the volume change is too small, 10 to the power minus 4, 10 to the power minus 3, volumetric strain is so small, you would not have expected their strength to increase. They would have thought, that their curves would be quite similar. So we did see that the strength is improved irrespective of how much the pore pressure is developed. So our expectation was higher the pore pressure development, more should be the strength improvement. But we did see strength improvement even in those soils where the pore pressure was less. Now this again comes out to be the structure of the soil. Remember we said HS and GS, these are the soils which are more angular, and BS is rounded. Rounded one, I did not discuss those curves. Their improvement was less compared to the angular ones. So angular one, it's expected that due to cyclic loading, even at constant volume, we would have expected certain greater interlocking among the soil. So more the interlocking, more the strength improvement, which could have been the reason that your HS, or I would say the angular particles, show much greater strength improvement compared to BS samples. Okay, that is one important conclusion. The second one was those soils in which our pore pressure development was less than or 0.75. We had a different set of improvement curves. So these curves represent improvement. So the vertical axis is the improvement, how much you have improved. Okay, it shows one different set of curves which are represented by, I have not written over here, I think it's on the next slide, but it represents a different set of curves, and those with RU or the pore pressure ratio more than 0.75, they represent a different kind of curves. So their representation is more like a power curve, and the previous one is more like a hyperbolic, close to hyperbolic, and this is close to power. So one limitation of this study is that at 0.75, so remember 0.75, the strength improvement beyond 0.75 is power, and strength improvement before 0.75 is hyperbolic. So there is a point of discontinuity at this value. Okay, so I do not know how much time do I have, but if I have some time, I can continue. Is anybody there? Or have I put everybody to sleep? I have, do you have another 10 minutes before I stop?
Yes, sir. Please continue.
Okay. Thank you.
Yes, sir.
So 1.5 hours include discussion. We need to give some time for discussion. That's
Yes.
important.
Yeah, that's
Discussion is
important.
important. So I want to spend time on discussion as well.
Sir, I think we will stop this session at 10:45. Then we will include the question answer session.
Okay, that is a good idea. That's a good idea. I have another
Yes.
10 minutes, close to 10 minutes.
Yes,
So,
sir.
coming back to this, so close to our pore pressure development and strength development, we looked at what is the stiffness, the change or the improvement in stiffness of the soil. So E value is the improvement in stiffness, and we did see that the improvement in stiffness also occurs for soils in which Ru is less than 0.75 and in which Ru is more than 0.75. So there is a difference in the two. Okay, but nonetheless, you do see some improvement. If you happen to see the paper, go through the paper, you'll find that uh, the strength improvement is based on a certain based on a certain you know results of standard triaxial test. So you are looking at improvement after the cyclic, but even with standard triaxial test, you still see you need some input data. So it's available in the paper. You're most welcome to see it. Now, when we looked at the improvement in stiffness, and the stiffness is our elastic modulus, right? So stiffness is the improvement in elastic modulus. You can also see an improvement. This is again as an offhand, which some of us have collected data. We are not only looking at the improvement because of post-cyclic loading, but what about improvement in case you have some air inside the soil deposit? So remember when we do compaction test, when we compact the soil at site for construction of embankment, it's not really a saturated embankment because of the air voids. Does it affect the cyclic response of the soil? So with this background, we looked at the effect on the modulus. So G is a shear modulus. It's similar to your Young's modulus. We looked at the different values of G with on unsaturated embankment. So embankment whose degree of saturation is maybe close to 0.9. If you look at the bottom figure, the degree of saturation of close to 0.9, you're still not far. Your Skempton's B parameter, again, if Skempton's B parameter of 1 tells us that the soil is saturated. If you do laboratory test, and if you have Skempton's B parameter less than 0.9, people advise you to do don't advise you to do a laboratory test. So we did go Skempton's B parameter quite significantly less than 0.9 because your degree of saturation is still 90%. If you look at this curve, even for 90% degree of saturation, you can you have, although your B parameter is hugely different, so but you can still use your conventional Tazargis theory. Conventional Tazargis theory is total stress equal to effective stress plus the pore water pressure, right? This is what we have studied. From our birth, we have been taking this as a tablet as a civil engineer. This equation is valid as long as your degree of saturation does not fall below a certain value, because then your pore air pressure comes into picture. So we did ensure that we did not allow the degree of saturation to fall in our samples, so that at least it makes our calculations simpler. So we looked at the liquefaction resistance. So vertical axis means how much is the improvement in the liquefaction resistance. So a liquefiable soil will be 1, and if you show an improvement of maybe 2 plus, I would say as an engineer, this is the best thing you can do to, to the market if you are able to improve it. Okay. So with this liquefaction improvement, you see all this data, we can string the data along a single line. Okay, along a single line, and our results which we got was a very simple equation based on this data curve fit was, the numerator is the, the numerator is the, what is the new value or the improvement value, and the denominator is the, without this, without accounting for the unsaturated soils which are used for compaction. So you do see some improvement. In fact, this 10 minus 9 SR is a simple expression which can be used to estimate what is the level of improvement. That was the liquefaction, number of cycles to improvement. These curves show the improvement in the shear modulus G value. You do see that even the shear modulus gets improved. I will not discuss the results, but there is improvement even in shear modulus as the degree of saturation is reduced to maybe 0.9 or so. Okay, I will skip this result and go directly. I think go directly to, yes, this curve over here. These sets of results. Now with desaturation, one important thing which, if you're a soil mechanics person, you should know is that the soil, the behavior of the soil becomes slightly over consolidated. So if I was looking at these curves, and if I follow these curves, this is the starting point, it goes up, and then over here it takes a left turn and comes down. If you look at it, the left turn is slightly above this reddish line. If it is on the reddish line, I would say the soil behavior is more like normally consolidated. But because it has crossed the reddish line, or I would say it appears, this is an important word, appears to cross the reddish line. It cannot cross because the reddish line is on a different plane. So if I say the white line is on your laptop screen or on your mobile screen, the reddish line is somewhere behind the screen. So it's on a different plane altogether. So what you see is that it exceeds or it crosses the reddish line, meaning the soil behavior is more like over consolidated. So with unsaturated embankment, the same soil will behave like an over consolidated soil. Okay, this is again one conclusion, or I would say this is the concluding slide. I will skip this and I think I'll go directly to my conclusion. So one important thing which we have observed is, yes, soil plasticity does affect the pore pressure generation. Both the power and hyperbolic empirical models have their limitation. There are limitation to this. You can achieve reasonable success by using a degradation parameter. So this is something which is possible. And the last is the angular grains, which cannot be in conventional design. We can't use that in dynamic testing, of course, but rearrangement of angular grains at constant volume did result in improvement. So even when the volumetric strains were small, the angular particles did help in improvement of the soil after the cyclic loading. So with this, I'd like to thank you for listening to me patiently. If there are questions, I would be very happy to take them up. So I have to see the chat window. Can I stop sharing? I think then I'll see the chat window.
Yes, sir, you can stop.
Participants are requested to send their questions if there are any, or they may raise their hands as well.
I have reached up to 10:47 a.m. I'm just looking at the, I think.
Yes, so we have.
I think I am not able to see. There is any question if it is there in the chat. Could you help me in if there is a question, because there are a lot of questions which are addressed to you as an organizer, but I don't.
Sir, as of now, there is no question.
Oh, okay.
Yeah,
Because
actually, I have one question. Yeah.
Yes, please go ahead.
Yeah, thanks, Professor Juneja, for the nice presentation. So,
I have reached up to 10:47 a.m.
yeah, I just wanted to actually ask about the, because you have what you said about it's the post-cyclic static response of the sands and cells. So how do you see the sands and cells responding to such type of loading when there is cyclic loading applied, not static?
I'm sorry, post-cyclic loading to what soil?
So if it is not static loading after liquefaction, or if it is not liquefying, you have applied static loading. So what about if we apply the cyclic loading once again?
Okay, so it's like, after one earthquake or one set of cyclic loading has occurred, then you have some drainage, and then you do another set of cyclic loading.
Yes, yeah.
So I think this is one thing which we did cover up in our research. So what we did was a set of maybe 1,000 cycles, then allowed drainage, and then another set of 1,000 cycles, then allowed drainage, and this thing continued for maybe 10 or maybe 15 set of cycles. So maybe to answer to this is, if you do one set of maybe 1,000 cycles and maybe 100 cycles in 10 sets. So our finding is, as long as your RU value is small, your final result is the same. Okay, this is one thing which we noticed, but obviously this was only limited to our kind of results. I have a slide which I can in fact share. It's on the PPT itself. If I do remember putting this slide. Yeah, I think this was it. So multiple load cycles is where you see this. If you can see this horizontal thing, just a second. What you see is, for example, over here you have close to 100 cycles. Sorry, you have 100 cycles, one set, and the same soil is now at a second set you have applied to maybe another set of cycles. So you do see improvement. So from 1.1 it has gone to 1.2. The same thing, we did 10,000 cycles, one set, second set, you do see some change. Although we did not explore too much on the right side, yes, there is 1,000 and probably we did 4 or 5 sets. There is also a 10 stage over here. So you do see improvement, but like I said, it depends upon what kind of pore pressures were developed and what kind of soil are you using. All right.
Yeah, thank you, sir. Yeah.
We have Majid Hussain probably has some question. You can ask your question.
Yeah, it was me actually asking the last question. Yeah.
All right, Nasir Islam. Nasir sir, please go ahead. Unmute
Hello.
yourself.
Can you hear me?
Yes. You are audible.
Good morning to all of you. First of all, congratulations to NIT Srinagar organizers for conducting this informative session. Next, my sincere gratitude to Professor Ashish Juneja sir for sharing his valuable time and experience with us. Sir, my question to you would be that has there been sort of the case encountered where there has been a comparison of the statistical analysis, like following the IS 1893 or by the seed and Idris et al. With the dynamic analysis, like using the Sheik table? If yes, then have you found any sort of the variations in those?
Now, can you tell me which particular aspect of you're looking at, or you want to ask about this?
Liquefaction assessment, sir.
Oh, so I think if you want to see such a thing, there is a paper which a comparison has been done, because seed and egress has been there has been a lot of changes to the original seed and egress work on liquefaction when you need to evaluate liquefaction potential.
Right.
There is a nice paper which has come out, I think, over about 2 decades back on this, and maybe you can refer to that, because it does add on to some of the improvement made into the original paper. If you want, I can, if you can just send me your email ID, maybe I can share the link to that paper.
Sure,
That
sir.
is much better. I think it shows what, and in the IS code, it has not, I think there's no, it has not come out clearly on the IS code, even in what to talk about the latest one. I think even IS code has not come out with any changes since the original seed and egress. We are yet to
Right, sir.
change.
There has been.
I think
Right, sir.
even the latest version of IS code, I have not seen it, if there is anything come out. But as far as my knowledge, it is still not out. But you can
Okay.
refer to that paper, because in most of the design which they follow, which we follow for liquefaction analysis, you do use refer to that paper, and it's become like a Bible, or I would say like a Quran for us.
Sure, sir. I will get that, sir.
Yep.
Thank you, sir. Thanks a lot.
Okay, any other? There's one question. One of the participants is asking about, sir. We generally do this study for granular soils like sands. What is the relevance of studying dynamic behavior in case of fine-grained soils? So, for example, a soil with predominant silt content. Is it what's the significance of doing dynamic study on such soils?
I mean, see, let me just start by looking at people initially, even these days, they say that, let me not speak about silt alone. Let me go to an extreme that, you're speaking about maybe clay. So people till even, even quite a learned people, they used to think that, clays under, dynamic loading will never liquefy, because the cohesion component, or the, the bonding helps under, even if the effective stress becomes zero due to liquefaction, the bonding helps it to retain its strength. So this is the thought process which many people have used or have followed, even until some of the more recent earthquakes, and they kind of, I hope they have changed, because even clays are known to sensitive clays particular, they can easily liquefy. So it is not only the sand which you are after, but also if you speak about liquefaction, clays also is an important topic. So silt, because they lie somewhere in between, it will be inappropriate to ignore them, first of all. And if I'm not speaking about liquefaction, if I just speak about dynamic response, because there is earthquake occurs maybe once in a year, but 99% of times you are interested in is under machine foundation, what is the response of the soil under bridges. For example, now metro is coming up in a lot of places. Metro, the towers of metro towers, I'll give you an example. In Nagpur, if you have heard, Nagpur is in Maharashtra. There is a metro, metro is coming up in Nagpur. And close to one metro line, there is a laboratory with quite sensitive equipment, which is sensitive to vibrations. So they were keen to know whether the metro which goes adjacent to into it whether those vibrations will affect their equipment, because those equipment are costly. And so again, it is not necessary liquefaction alone can be a research research idea or research thought. There are a number of other places where dynamic loading does come into picture. So in those cases, not only sand but also in silt, clay is important. If you have an embankment constructed of silty soil, then under dynamic loading, it's pretty important to know whether the soil embankment under loading will will sustain the higher load or not sustain the higher load. So there are a number of cases, examples. So I would say not only say sand but number of cases.
Thank you very much, sir. Any other question? I think even the time is over. I think we are done with the discussion session also. Professor BME, sir, if they want to say something as end note. Sir, are you there?
Am I audible?
Yes, sir,
Am
you
I
are.
audible?
You are, sir.
Thank you very much. First of all, I thank Professor Juneja sir for very informative and interesting presentations, and the test results we have seen very interesting. And I hope that the participants, particularly PhD students, would be more oriented towards when seeing the stress paths and some idea about critical state soil mechanics will really help them in their research work. I also thank participants who have taken their time and attended this short-term course, and hope that they are very much benefited from this course onwards. And I also thank my PhD students who are working tirelessly for this and managing this program well in time. And finally, once again, I thank all the dignitaries in the morning who attended this inauguration session, as well as my Juneja sir. Once again, sir, thank you very much, sir, for this presentation and accepting our invitation for this course. I may also hope in future for your this valuable knowledge, which will be very helpful for us and for research scholars in future. Thank you, sir.
Thank you.
Nadeem, so you can wind up.
All right, sir. Thanks a lot, sir. Again, thank you very much from the Geotechnical Engineering Division. A request to all the participants to kindly fill the feedback form that we have attached in the chat box. That would be counted as your attendance, and it's mandatory for you to fill this the same link. It will be sent for other sessions also, so you are supposed to fill it regularly. Moreover, tomorrow we'll join at 9:30 sharp. The speaker would be Dr. Sarat Kumar Das, Professor, Department of Civil Engineering, IIT, Dhanabad, Jharkhand. So the topic would be evolutionary optimization methods in geotechnical engineering. Very interesting topic. So see you tomorrow. For now, we are winding it up. Thank you for your patience. Thank you for being with us. Thank you.
Thank you all. Thank you all.
So will we get the PPT for the session?
For PPT, if we get approval from the speaker, then only it will be possible.
Okay. So thank you for the session. It was very interesting and very informative.
Thank you.
Thank you.
Thank you for your nice words.
Yes.
Thank you. All right. Winding it up. Thank you.
Thank you, Nadeem sir. Good day.